Let's see. Let me see if the audio is good now. It looks like the audio is good, but let's see. I think the audio is good. Let's see. Okay. Okay, now the audio is good. Perfect. Let me see if the audio is good now. It looks like the audio is good, but let's see. Okay, now the audio is good. We're going to start. Okay. So buckle up. This is going to be a very interesting one. Um, let's start. Okay. The first problem we have is that which of the following pollutants is not a criteria pollutant as defined by the National Ambient Air Quality Standard? Okay. The National Ambient Air Quality Standard. Um, you got to know what that is. Probably they are for air quality and control. So they are called the National Ambient Air Quality Standard. So they're asking on which of the pollutants is not a defined is not a defined criteria. So which of these won't be considered as a pollutant? Okay. Um, criteria carbon monoxide. Carbon monoxide is not a defined pollutant criteria. So obviously, it's going to be our answer because lead is a defined pollutant. Nitrogen dioxide is a defined pollutant. Coarse fine particles because they can go into our nose and everything. So dust and all this stuff that define pollutant. So which of the following is not? It's going to be carbon monoxide, okay? Because the lead, dust, NO2, they're all defined what's called pollutants, okay? So the answer is going to be A. Two, carbon monoxide has been mentioned to have, sorry, I have a note right on my audio screen, so I'll be, because I've solved this before. So we say carbon monoxide has been measured in an automotive repair garage at 9 ppm, which is the same as part per million by volume. The garage has a pressure of 1 standard atmosphere, a temperature of 16 degrees Celsius. Most nearly, what is the observed concentration? So for this question, okay, for this question, they gave us what? They gave us the ppmv as 9 part per million per volume. They gave us what? They gave us the pressure as 1 atmosphere. And they gave us what? They gave us the temperature as 16 what? Degrees Celsius. So once we have this, what's the first thing that goes to our head? The first thing that goes to my head is what? Ideal gas law, which is what? PV equals to nRT. Now we know in this ideal gas law, we know we have P right here, we have V right here, and we're what? We're looking for the most nearly observed concentration. So how are we going to get the most nearly observed concentration? How we're going to get this? Because we know R is a constant, and we know we have temperature. So we have all this. Let me put all of them. We asterisk. We have all this stuff. So if we want to get the concentration, we have to break down the N, which is number of moles, and we know N in this case can be also given as moles is equals to mass all over molecular weight. Okay, and moles is mass all over molecular weight. So when we have this, our formula is going to be PV equals to mass all over the molecular weight dot RT. Okay, now we already have this formula. What are we looking for? We're looking for what? We're looking for M right here, which is the observed concentration. So we're looking for M right here. So M is equals to PV, okay, over R over mw dot t. Okay, because we're asking most nearly what is the observed concentration, which is m. This is our concentration m. Okay, now we already have that. What we're going to do next, our molecular weight of carbon monoxide. Carbon monoxide is what? Carbon monoxide is CO. Yeah, CO is what? C is 12 and oxygen is what? 16. So this is what? 28. Okay? So this is 28. So we're looking at what is our observed concentration, which is M. So we already have P. We already have the molecular weight of CO. We already have this molecular weight. We have ppv, which is our volume part per million, and this can also be our volume part per million, which can is going to be equals to 9 multiplied by 10 raised to power minus 6. Okay, because meter cube meter cube, we're going to use it. This is still going to cancel because it has no unit, but this is what we're going to use. 1 atmosphere is correct. Our T is what in degrees Celsius. We have to convert our T to what? We have to convert it to we have to convert our T to what? Kelvin. So this is equals to 16 plus 273, which is going to be. I have my calculator right here. So 16 plus 273, which is going to be 289. Okay, 289 Kelvin. Now we know R according to the gas constant. Okay, R according to our gas constant based on our formula, and we can find this R. We can find this R. I have this FE handbook. In this FE handbook, we can find this R. Uh, it's gonna be if we search R. Okay, this is. I believe it should be around in the first page where all the units are. Yeah, it should be around this page. Constant, gas constant. Okay, yeah, you see the gas constant. So the gas constant we're going to use for this is going to be 8.314. We have 8.314. This one Kelvin, what's it called, Pascal, meter cube, and all this stuff. So if we're using 8.314 if we're using 8.314 kilopascals, meter cubes, kilomole per Kelvin, we have to convert our temperature from atm, which is atmosphere, to kilopascals. Okay, so if we're converting our temperature um, from atmospheres to kilopascals, we have to say the most stuff is about conversion. We have to go to this table, and when we go to this table, we're going to see what's the relationship, okay, for atmosphere to kilopascals. Um, we have pascals right here. We have atmosphere right here. Mm, when I was doing this, I just googled it. I didn't really use this FE, but in the exam, we have to use this. We have to use this FE handbook. So trying to make sure everything we're doing comes from here. Mm, meant to be, yeah. So it's gonna be somewhere, yeah, but Probably I'm not looking right. I don't want to slow down this because while running on time. So the conversion for that, if we want to convert kilopascals, this to kilopascals, what we're going to do is that we're just going to multiply this by 101.3 kilopascals. And I'm going to do all the conversion down here. So since we're using this formula right here, our concentration M is going to be 1 atmosphere multiplied by 101.3 kilopascals multiplied by 9.0 times 10 raised to power negative 6 meter cube, okay, multiplied by what? Now we're doing all this multiplication. Now the next thing we're gonna do is that we're gonna multiply it by 8,000 milligram times gram and multiply it by 8,000 mole per kilomole. Because what? I will show you why we're doing this. Let's divide it and I'll show you why we're multiplying this by this. So we have R as 8.314 kilopascals the meter cube over 28.01 gram per mole. Okay? Multiply by 16 plus 273. What is it? Kelvin. So I always do dimension consistency. Everything needs to cancel out. That's my goal. Because I know our concentration, I'm trying to make our concentration in milligrams per meter cube. Okay, so that's why I'm converting these grams we have to milligrams. Okay, and I'm converting kilomoles to moles. Okay, so these grams right there we converted. This is going to cancel this. Okay, and sorry, I'm converting moles to kilomoles. So this is going to cancel this. Okay, so what do we have? What do we have next? This is kilopascal meter cube. I forgot to. This whole formula is kilomoles per Kelvin. So this is going to cancel this. Okay, you have to get rid of the Kelvin, right? This kilopascals is going to cancel this kilopascals. This meter cube is going to cancel this meter cube. Um, we have, what else do we have that needs to be canceled? Um, yeah, Kevin right here, sorry, is gonna cancel the Kevin like right here. So what we're left is we're gonna be left in meter cube and we're gonna get left in milligrams, okay? Because our concentration is gonna be the mass over the volume. So right here, the concentration of this is gonna be, once we do all this and do all the multiplication and everything, we're gonna have approximately 11 milligrams per meter cube, which is A right here. Okay, that's how we solve this. Very easy. We use the ideal gas law, solve for M, and we do all this. The main stuff that gets you in the FP exam is the conversion. That is the main stuff that gets him. Because the reason why I'm converted to milligrams per meter cube instead of leaving it in what's it called grams is because in our formula is it's gonna be milligram. So I had to do all the conversion to milligrams per meter cube, and also we have to convert what's it called? Uh, get rid of this get rid of these kilomoles too. So most stuff is just all conversion. This was just all conversion, and you have to be very um used to it to solve these equations. Okay, so I'm gonna clear my screen right here. Honestly, I can just go down. I'll just go down. So our next question, question two. Oh, this was question two. Our next question is question three. What does VOC stand for? Volatile organic compounds. So VOC are volatile organic compounds like alcohol, all these compounds that when you expose them to the atmosphere, they kind of like evaporate so quickly. So that's what VOC stands for, volatile organic compound. As for equation, I believe every chemist should know this. Represent the equation to form acid rain. This is very easy one. Is SO3 plus water, not SO2, not sulfur dioxide, is sulfur trioxide. SO3 plus water is equals to H2SO4. This is the formation of what's it called, of acid rain. Okay. Next question we have is an incomplete combustion of fossil fuel. An incomplete combustion of fossil fuel, that means there was not enough oxygen to supply. So normally combustion has this formula of we have, let's say, carbon plus oxygen give us CO2. CO2 is always the final product. Sometimes it's gonna be, if you have a carbon, if you have like a hydro compound like methane plus this is gonna be CO2 plus water. When you balance this equation, you're going to have something more different. But this is just a general formula of combustion. But most times our main product is CO2, okay, for combustion. Now, when there's an incomplete combustion, that means there's not enough oxygen. Instead of getting CO2, we're going to get CO, which is carbon monoxide. So our answer is going to be C. You know about that. This is the first time I'm doing a marathon, so it's getting to me. So we're almost done with this equation. So they say the minimum particle generally considered for inhale hazard. The answer here is 10 micrometers. If you look at the quality for like inhale particle, is 10. That is the minimum amount that we're going to be considered to go inhale. So generally particles that are generally less than 10 micrometers in size are designated they're okay to be inhalable. Um, um, sorry, consider less than 10 are designated to be hazard because we're looking for minimum and general considered to be inhalable. So yeah. So the next question we have, which of the following device is the least effective at removing fly flash particles with diameter of 1 micrometers? The answer is gonna be the what's it called? It's not gonna be electrostatic precipitators. It's not gonna be fabric Bauhaus. It's gonna be a air cyclone because air cyclone has to deal with gravity. And if we have a fly ash, that means it's not as heavy as gravity. So gravity is not gonna work because the diameter is so small as 1 micrometer. So the answer is gonna be air cyclone because it relies heavily on gravitational and centrifugal force to collect the particles, okay, small particles, okay. So let's go to the next one. So the next one, wine discharge water and quality. That is our next questions. Wine discharge water and quality. So this is gonna be longer than the previous one. So let's get it started. Now they said, which is the most nearly equivalent weight of aluminium sulfate? Now the first thing we're gonna do was equivalent weight. So equivalent weight will represent as EW equals to the molecular weight divided by the oxidation number. So that's the first thing we're gonna do. So now we know this. What we're gonna do, we have to find the molecular weight of aluminium. Okay. So the molecular weight of aluminium sulfate is going to be, how many aluminiums do we have here? We have two aluminiums, right? Plus this is going to multiply by everything in the bracket. So we're going to have two. We're going to have, sorry, SO43. Okay. So this is going to multiply. So we're going to have 3 sulfur molecular weight plus 3 times 4 is going to be 12 oxygen. So we know aluminium is what? 26.981 or 27. Sulfur is what? 32. And we know oxygen is what? Oxygen is 12. So what we're going to do, we're going to multiply all these things. So we're going to have the molecular weight of aluminium SO4 3 is equals to 2 multiplied by 26.981 plus 3 multiplied by 32 plus 12 multiplied by what? Oxygen is what? 16. My bad. This is meant to be 16. I think something was off. 16. So when we do all this, we're going to have approximately 342 gram per mole. So we have 342 gram per mole. So what we're going to do, the oxidation number of what? The oxidation number of aluminium ion. So aluminium ion, based on the periodic table, has an oxidation number of 3 plus. So since we have 2 aluminium, so the oxidation number is going to be what? 6 plus. So we're going to have 342 divided by 6. And when we do that, it's going to be closest to 57, okay, gram per mole, which is A. Very, very easy. One thing we have to know is that molecular equivalent weight is equals to molecular weight divided by the oxidation number. And once we know that, everything gets so easy and simple, okay? So the next question we're going to have is a water sample contains 57 milligrams per liter. So that is the concentration of phosphate measured as a substance. What is the concentration of CaCO3? Um, Now for this question, I'm looking for the concentration of CaCO3. So I want to show you guys where I'm getting all this from. Um, Let me just type um, EW. Probably it's gonna pop it out well. Oh, nice. It's meant to show you all this equivalent weight. I want to show you guys what this equivalent weight stuff is. So in the FE exam, you guys can pull up this reference document and know where to find it. Let me just do. Because everything is here. Everything is here. Let's see. Where is this stuff? Let me let me go up to air quality. It's meant to be here because I found it from here. So it's been a while since I solved this, but I'm trying to look for where I can get where's the keyword I was looking for when I found it. Let me see quality. Let me see. This topic is discharge. What's the equivalent weight? Equivalent weight. So let me try looking at equivalent weight. Um, mm, 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 mm. Where did this go? Oh well, you guys have to look for it in the reference table. I don't know where it went to, so no time to wait. But luckily, I have my notes, so which is good. So for these, they said, what is the most nearly concentration of CaCO3? So we're trying to look for the concentration of CaCO3. We have the water sample contains 57 milligrams per liter of phosphate. So the water contains 57 milligrams per liter of phosphate. We're looking for the most nearly concentration. Measure this 57 of phosphate measured in the substance, and we're looking for the what is the most nearly concentration of concentration at CaCO3. So what we're gonna do first is that we're gonna find the equivalent weight of the phosphate, and once we have the equivalent weight of the phosphate, we're gonna find the concentration of CaCO3, and the concentration of CaCO3 is gonna be C as CaCO3, okay? Because that's what we're looking for. It's gonna be C as substance, the concentration of C as substance multiplied by the equivalent weight of CaCO3 CaCO3 divided by the equivalent weight of phosphate, because we are looking for the concentration of CaCO3, okay, and we're going to find, okay, what's the concentration of C in substance, because they say a water sample contains 57 milligrams per liter. So the concentration of C, the substance, contains 57 milligrams of phosphate. So the concentration of phosphate, which we're using as C right now, in the substance is what Pa4 is what 57. So we're looking for what's the concentration of CaCO3. So it's more like I always put it more like a dimensional stuff. And there's another trick we can use. There's another other trick we can use, and I'm going to show you the other trick instead of going through this route. There's another trick I'm going to teach you that you're going to use, but we have to find the equivalent weight first. Okay. So first, we're looking for the equivalent weight right here. So how we're going to find the equivalent weight of phosphate? When the equivalent weight is molecular weight all over oxidation number. So for phosphate right here, the molecular weight of phosphate right here is going to be 94.97 is our molecular weight, and the oxidation number which I circled right here is going to be 3. So we're going to have 31.657 gram per mole. So we'll do the same for the equivalent weight of CaCO3. So for CaCO3, for this, our molecular weight is going to be around 100, and our what's it called? About calcium is what 2 plus. So we're going to divide it by 2. So we're going to have around 50 gram per mole. Okay. Now we have this. We're going to use this formula. This is how I'm going to do it. This is another trick we can use if we don't want to do this. We're going to have 57 milligrams per liter of phosphate is equals to what? 31.657 gram per mole equivalent weight. So X of CaCO3, what concentration of CaCO3 is equal to 50 grams, okay? Is equal to 50 grams per mole, because molar mass is grams per mole. So if we do this, what we're going to do, we're going to cross multiply, okay? So X is going to be equal to 90.21 milligrams per liter. That's our concentration. That's another way of doing this. It's obviously that formula, okay? That's how we're going to solve. We're going to find the equivalent weight of both of them. I'm going to go equate both of them. We're going to find the equivalent weight of both of them. I'm going to equate this and we're going to find our answer. Okay. So the same stuff, and this is under the discharge and air quality, water discharge and water quality. Okay. So our next one, we're going to have the alkalinity of water was determined to be 200 milligrams per liter as CaCO3. So if the nitric acid weight is 63 grams per mole, so that's the molecular weight, and solution with acid is 35 milligrams per liter, that is the concentration of CaCO3 with acid, and this is the concentration of CaCO3 in water. Okay, alkaline of water was determined to 200, so water concentration is determined to be this. Is available. Most nearly how much solution will be required to completely neutralize the water. So this is a very tricky one. Okay. So yeah, they gave us the alkalinity of water was determined to be 200 milligrams per liter. Okay. So the concentration of water in CaCO3 as CaCO3. So the concentration of water as CaCO3 is what? 200 milligrams per liter. The nitric acid molecular weight of HNO3 is what they gave us. It's 63 grams per mole solution. And they said the acidity, the solution with an acidity of 35 milligrams as CaCO3. So the concentration of acid as CaCO3 is what? The concentration of acid as CaCO3 is 35 milligrams per liter. Okay. And they also said most nearly how much acid solution would be required to completely neutralize 700 liter of water. So we have water volume at 700 liter. I was looking for the concentration of acid solution that will completely neutralize the water. So how much acid solution will be looking at? So we're looking at the volume of the acid solution. This is what we're looking at. So in this scenario, our molecular weight of which is HNO3 is completely used to fool us. So our formula we're going to look for, formula we're going to do is CV C1V1 equals to C2V2. Okay? C1V1 equals C2V2. But the same as changing concentration, let's change the concentration of this. So this is the same stuff we're going to use. So since we have this, we know that we're looking at the volume of the acid. So let's say the volume of the acid is V2. Let's call this volume of the acid. So V2 is going to give us changes C V1 over changes C2. So we have the concentration of what? We have the concentration C1. We have the concentration of our water in the alkaline solution. Our concentration of water as CaCO3, the alkalinity solution as 200 milligrams per liter. Okay, we have that. I will see what they change the concentration minus 0 milligrams per liter because nothing changed. Multiply by the volume, which is 700 liters. And we have what? Change the concentration of 2, which is what? 35 milligrams per liter over 0 milligrams per liter because they completely neutralize. Okay. So we have this. And we're looking at what? We're looking at the volume of the acid because they contribute. We're looking at the volume of the acid V2. So all these, this is going to cancel. This is going to cancel. This is going to cancel. So all these milligrams per liter. So if all these milligrams per liter, so this is going to cancel all this. I'm looking at this. So this is going to be fine. This is going to be fine. So if this cancel this, we're going to left with 200 times 700 liters over 35. So V2 is going to give us 4,000 liters. Okay. So this is how we solve it. Very easy, very simple, very straightforward, and very easy. Let's go to the next one. I told you guys this is going to be a marathon. That's not going to be the end. We're going to come back after a short break and we're going to continue and solve another 4 more chapters. Okay. My plan is to host this stream every day and solve one chapter for per day. Because it's gonna pace me and it's also gonna pace you guys and just compressing everything in one stream. But we got to catch up from what we left, so I'm gonna do 4 chapters for today. Okay, so we have for the next one a water analysis for lake water. The most crazy chapter is going to be the last one, which is going to be the engineering economics, or is it going to be a lot of solution? I don't know if I should. I was thinking of just continuing with this and solve 3 chapter in this round and wait for the next one and solve the whole engineering economics for the next one because I believe that might be a better strategy. Because it's like 20 equations there. Okay, and there's one other question I'm not sure how to solve, which the last one, which I'm going to look at before I start new stream. So we say water analysis of lake water has the result of this. Okay, with with values reported. So what they want us to find. Okay. So they say what is the hardness? So if we're looking for the hardness of water normally, if we're looking for the hardness of water, it normally is as a result of calcium ions, iron ions, and magnesium ions. So these 3 ions, calcium, iron, and magnesium, I call them same, the same ions. So these same ions are mostly the result of the hardness of water. So yeah, we have the calcium ion concentration as 127.5 milligrams per liter. Okay, we have we're gonna we have the magnesium ion concentration as 43.5 milligrams per liter, and we have the iron concentration as 0.107 milligrams per liter. So we're just gonna add all this. Okay, so once we add all this, we're gonna be have a 171.107 milligrams per liter. So once we add all this, we have 171, which is the same as 170. So that is B. Okay, that is B right here. So the hardness of water consists of 3 major ions, which are also called sim, and that's how we're going to solve this. So equation 5 is kind of similar to what we had in equation 3, but in this formula, equation 3 they completely neutralized, so the concentration didn't change. But in equation 5, they said um, equation 5 we are looking for, let me just read it. Water has a carbonate hardness of 92 milligrams per liter as CaCO3. Most what dose of lime CaO as a substance will be should be added in water to reduce the hardness by 30 milligrams. So we're looking for what's it called, the dose of lime that should be added to reduce water to reduce the hardness to 30 milligrams. So now this is a bit tricky. Sorry, I kind of messed the question up. This is a bit tricky because now we're looking at we're looking at most nearly what dose of lime should be added to reduce the hardness of water. So in this question, we're not just looking at what's it called? We're not just looking at we're not just looking at to find like what's it called, the concentration. We're looking at the dose of lime that should be added to reduce it. So we're gonna use the equivalent weight formula here, and we're gonna use that to also relate to get the concentration. But unlike most of the equations, we use the equivalent weight formula. We don't have the concentration of lime in this. So we have to find the concentration of lime in this. So for us to find the concentration of lime in this, because know fully well, we're looking at water has a carbonate hardness of 92 milligram as CaCO3. So we have water as CaCO3. So change the concentration of water as CaCO3 is equals to 92 milligrams per liter as CaCO3. We have what mostly nearly is the dose in lime. So we're looking at the dose in lime, which I can also do like the concentration in lime too. We can do it, but we'll represent it as D, dose in lime, dose in lime. So those are CaO. We're looking for this. Okay? We're looking for this. A substance should be added in water to reduce the hardness by 30 milligrams per liter. So here the concentration changed by 30 milligrams per liter. So the concentration, so we have the concentration changed to 30 milligrams per liter. Okay, so um we have the concentration right here, changed from 92 minus 30 milligrams per liter. So we have a change in concentration as 62 milligrams per liter. Okay, so the concentration changed to 30 milligrams. So we have concentration to 62 milligrams per liter. So we're going to use the formula change in C times V1 equals to change in C times V2, and change in C1 C2, and this is equals to dose of lime. Okay, so change in C2 is equals to 62. That is a standard of 1 liter over 1 liter. So this is equal to 62. Okay, so this is going to give us 62 milligrams per liter. So that's our change in of um this is our concentration of dosage of lime. But no, all this concentration we're looking at the concentration, we're looking at dose of lime as CaO. But now they're asking us what it is as a substance. Okay? Because if you look at this previous concentration, when we see as water 50 as being measured as a substance, what is mostly nearly the concentration as CaCO3. Okay? So in this question, we have the concentration as substance. Now we're looking at the concentration as CaCO3. That's what we use. But yeah, we have the concentration of lime as CaO. And now we're looking at the concentration as a substance. So we're going to use a similar route as we used to solve this, but in a reverse direction. When we have any question that we have the concentration as a particular compound and they ask what's the concentration of substance, that is a trick that we're going to use the equivalent weight, any other stuff. But for us to solve it, we have to know what? The equivalent weight. Okay? We have to know the equivalent weight of CaO. Okay? So we have to solve for the equivalent weight of CaO. And when we solve for the equivalent weight of CaO, we're going to relate to that with the equivalent weight of CaCO3. Okay? Because this dosage we solve is for, oh my bad, this dosage we solve is for CaCO3. Okay? We found the dosage of CaCO3. Okay? We found the dosage of CaCO3. Now we have to know for the substance of CaO. That's when we're going to use the equivalent weight. Okay? Because we're dealing with two substances. Okay? But we have the dosage of lime in COCO3. So since we're looking at lime, we have the dosage of lime in COCO3. We're looking for the dosage of lime in CaO. Sorry, this was correct. We're looking at the dosage of lime in CaO. Okay, so we're looking at the dose of lime per year in CaO. This is what we're looking for. We already have the dosage of lime in CaCO3, so the dose of lime in CaCO3 is 62 milligrams per liter. So first we have to find the equivalent weight of lime. Okay, we have to find the equivalent weight of lime in CaO, and we have to do the same the equivalent weight of lime in CaCO3. I already saw for that, which is no equivalent weight, is molecular weight all over oxidation number. I already saw for that is 56.07. Let me just solve for everything. So this is what we're looking for right now. We're looking for this A, and we're looking for this B. So let's get for A. Equivalent weight of lime is going to be in CaO. Let's see, CaO is going to be the molecular weight of CaO is, when we solve for it, we're going to have 40.7078 plus 15.99, which is also equal to 16. We're going to have 57.07. That's the molecular weight of CaO. So divide by the oxidation number, calcium is 2 plus, so we have 57.07 divided by 2, which is equal to 28.039. So now we have the molecular weight of CaO. So next we're going to have, that means we have the equivalent weight of CaO. Equivalent weight of CaO is this. So we have to find the equivalent weight of CaCO3. You know, we found it before, and it was around 50. So now we have that. We're going to say do our relationship. So 50 milligrams per liter gave us what? 62. So 50 gram per mole, sorry, gram per mole molecular weight gave us 62 milligrams per liter. So 28.039 is going to give us X 1 milligrams per liter because we're dealing with two substances. So 28.039 is going to give us X 1 milligrams per liter. So when we multiply that, it's going to give us 28.039 multiplied by 62 all over 50. So X is equal to give us 34.7 milligrams per liter, which is similar to 35. So what we did basically, we used our initial formula, change the V, change the C, to give us the concentration of lime in CaCO3. So since we're dealing with two substances, so we use the equivalent weight of one substance. We found the equivalent weight, and we're going to relate the two substances, and we're going to find it. So we use equivalent weight mostly when we have two substances, and when we have similar substances, and we're looking for volume or concentration. Then we can use the changing concentration of our change in volume. So basically, that's how we solved it. Um, you can watch this video like 2, 3 times if you have any other question, but That's how we solved it. So we're gonna move on to the next. Um, Next question is, which of the following generally not attributed to hardness of water? Scum in the rings of the bathtub. Yes, hardness of water. The biggest difference between hardness of water, hard water and soft water, is that hard water don't lather. What I mean by lather, when you're taking a shower and you put soap and you kind of sponge it, you're gonna see like a foamy stuff. And in hard water, don't have this foamy stuff. So that's one of the big difference with it. So foaming our clothes when washed is definitely the answer. Scale build up, yeah, it stains on the porcelain, but yeah, that's hard water. So it doesn't lather. So answer is definitely C. We have a fate and transfer study was performed on phosphorus in a small pond. Biological process in the pond biotar converts phosphorus to non-bioavailable form at a rate of 22% per year. Okay. Recycling of sediment phosphorus by rooted plant and anaerobic condition in a hypolimnion convert 12% per year of non-bioavailable phosphorus back to bioavailable forms. Runoff into the water evaporate during the year. So no change in the pond volume. Which of the following actions would best reduce the phosphorus accumulation in the pond? Okay, so adding chemicals to precipitate phosphorus in the pond, no, it's not going to remove. So you're just putting chemicals to precipitate phosphorus. That means phosphorus will still be concentrated in the pond because precipitation, unless we filter it, is still right there. Adding chemicals to combat with phosphorus in the pond, no, it's not going to reduce. We're just going to have a phosphorus compound. Reducing the phosphorus-based fertilizer in the surrounding of the field, yes, it's going to reduce because we are reducing the intake of phosphorus. So definitely C is our answer. Using natural-based detergent of around homes, nope, it's not going to reduce. It's not going to contribute anything. So definitely C is the answer. Hardness of water is caused by the presence of hardness of water is mostly caused by the presence of polyvalent metallic cations. Yes, so this is the answer. This is something every chemist should know. It's not caused by the absence of weakly acidic, no nitrate, no poly. It's caused by the presence of polyvalent metallic cations. So every chemist should know this. So let's go to the next one. Aquatic phosphorus recycling is significantly aided by recycling for aquatic phosphorus is significantly aided by um, believe it's I don't think it's not fungi, so it's probably gonna be I know it's microphytes and phytoplankton is part of it. I don't know about algae, so let me use cross elimination, this and this, this and this. So we have between C and D. I know it's not fungi, so it's definitely gonna be algae more part of it. So it's definitely gonna be C. Definitely gonna be C. Okay, we have more. Which of the following source can cause the color of water? Color of water. Definitely. Which of the following source cause color of water? Copper ions. Can it cause color of water? Does copper have any color? Let me check. Copper metal color. That is blue. Hmm. Okay, copper. That means copper has a color. Okay, if copper has a color, definitely it's gonna affect the color of water. Iron has a color. Magnesium has a color. Industrial colloidal solution can cause color because it makes it cloudy. So I'm gonna say it's D. All of it. Pretty sure it's D. 11. Which of the following process is used to measure the amount of acid in water? To measure the amount of acid in water, the process we normally use is titration, acid-based titration. This is very basic. All chemists should know this. Acid-based titration is definitely the answer. For the next question, we have the acidity of water is specified in terms of which of the following hydrogen ion H plus B. The manual had it wrong. They says DCA03 no is hydrogen ion, so 12 is the answer. Um, for the next one we have The National Primary Drinking Water Regulation applies to which of the following supply or servings at least as many as 15. So once we have 15, regulations start occurring. So it's A. The molar concentration of nitrogen phosphorus in an RED growth is 16 to 1. It's not 10 to 1, 16 to 1 is the answer D. These are all theoretical questions, so it's good. In water, excess amount of which of the following can contribute to metamoglobin or blue baby? Uh, I know blue baby is caused by excess amount of nitrates, so I'm gonna go with D. So that is the answer. Um, let's see if we can rush through the next one. Let me see how much industrial hygiene. Okay, industrial hygiene is only three questions. So we can rush through industrial hygiene. It's only three questions. Um, and this is one of the easiest part of chemical engineering. It's three questions, pretty easy. Um, let me try solve the whole stuff. DB, noise complaint, and the whole stuff. Um, so in this, I'm gonna try and see if I can find this in the manual for you guys. Um, sorry. The thing is, I found it last time I searched for SPL. Um, yep, I found the noise pollution. So this is what we're gonna use for this. This is very easy. It's gonna be very easy. Just pay attention. So a construction worker works in a 91 dB site for 3.5 hours and 86 dB site for 3 hours and 81 dB site for 1.5 hours. What is most nearly the noise dosage? Okay, if you want to find the noise dosage, let me pull this up again. So for the noise dosage, our formula is meant to be D 100 times something. It's meant to be M somewhere here. Let me pay more attention. Mm, 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 mm. Mm, 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 mm. Why is this? I don't think this updated. So if you want to find the noise dosing, the first thing we have to find is the exposure time limit. Now I'll show you how to find the exposure time limit. So if you want to find the exposure time limit, we're going to use mm, 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 mm. I don't know why the formulas are not here. They're meant to be here. I know in the exam they'll give you everything you want, but uh, I'm only seeing the SPL total. I'm looking for the formula for the exposure time limit. Okay, I don't think it's here. But the formula for the exposure time limit is T equals to 2H, which is in hours, 105 minus XPL divided by 5. Okay. And here they said the construction workers in 91 dB, so they gave us all our SPL. So for T1, T91, let's just call it T91 dB. T91, we have 2H over 105 minus 91 divided by 5. We have T 86 equals to 2H 105 minus 86 divided by 5. And T81 we have 2H 105 minus 81 divided by 5. When we solve for all these, we have 6.96 hours, we have 13.93 hours, and we have 27.86 hours. So this is the exposure um, time for the construction worker. So we have to get the noise dosage is 100 multiplied, this is the formula, by the summation of the um the time, which is CI, that that they were working for over the exposure time limit. Let's call it TI. So this equals to 100 multiplied by 3.5 over 6.96 hours. This is hours too, so they both cancel. Plus 3 divided by 13.93 hours, so they both cancel. Plus 1.5 over 27.86 hours, so they both cancel. So when we do this out dosage, it will give us 77%, which is B. I don't know why this is not here. So we have for the next one, um, we have the sound pressure level, which is SPL from the machine. Machine 1 is 91, and the sound pressure value machine 2 is 95, and sound pressure value machine 3 is 90 B. What is the nearly sound pressure level the workers is exposed to? So this one is pretty much gonna be simple because I think I saw SPL right here. So we're gonna use this SPL total formula to solve it. And we all know the SPL total formula from what I just showed you right there is 100 log 10 summation of 10 SPL over 10 with sound pressure exposure. So first, the SPL total is gonna be 100 log 10. We're gonna do the SPL for all these, which is going to 10 raised to power 91 over 10 plus 10 raised to power 95 over 10 plus 10 raised to power 93 over 10. All these are dB. All these are dB. 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 Okay. Once we're going to have it, solve all this, our XPL is equals to 98.07 dB. This was our exposure limit. So, okay. This is the last question before I take a break and come back for the next marathon. Okay. So in this question we have, during each walk, the sewage treatment of the plant, the workers are exposed to the noise from the sludge pump and a blower and a ventilation fan. No two pieces of equipment operate simultaneously, and all noise is at 100 hertz. Rated to dBA scale, and we're trying to solve. What are they trying to make us solve? Like, bro, we don't want this fine. So, according to the Established Safety and Health Occupation OSHA, it's, permissible noise exposure, the permissible exposure in each of the sewage plant. Okay, so first to solve this, we're gonna know the exposure time permitted. And from the exposure time permitted, we're gonna see if any of these matches. Okay, so I will find the exposure time permitted. Remember, the exposure time permitted is gonna be 2H 105 minus XPL, the exposure limit, divided by 5. So we have three of these. We have for this large pump, I'll just call them T96. T96 is equals to 2H 105 minus 96 over 5. T94 2H 105 minus 94 over 5. T98 2H 105 minus 98 over 5. So this is what 3.84H. 3.48H. No, no, no. So this was 3.48H. This was 4.59H. And this was 2.64H. Okay. So now we have that we're going to calculate for the um exposure limit. Now we have the exposure time limit. We're gonna do what we normally do: C over T, calculate for the number of exposure that was all happened. So we're gonna have C over T of all of them, summation of C over T, which is 2 all over 3.48. This is H. So this will all cancel, plus 3H over 4.59 H all cancel, plus 2H over 2.64 H all cancel. So this is going to be give us 2. Okay. Now we already have that. The next thing we're going to do is to go our total is 2. So we're looking for anyone that the summation of 2 is greater than. Okay. So let's look for the options. Let's say exceed because the time weighted average TWA exposed exceed 85. Nope, that's not true. All of them not exceeded because none of the permissible, so definitely exceeded because 2 is greater than everything. So exceeded because the sum of the fractional allowed exposure duration of sound exceed 1. Yes, this is 100% because 2 is greater than everything. So it definitely exceeded. So not exceeded is no, but it doesn't exceed because the time weighted average of exposure exceed 95. No, that's not the reason. Because the time weighted average for exposure, what's it called? The time weighted average for exposure is not the reason for that. Okay, so that's why the answer is C. So that's for industrial hygiene. I think what is next? Let me see if I can solve what is next. What is next is toxicology. Um, I look, you want to solve this. I look, you want to solve this, but I think we all need a break. So I'm going to end the stream from now, and we're going to come back and we're going to solve toxicology. It's going to be a very easy one, and then we're going to take another break and we're going to solve the big boy problem, which is the big boy is obviously engineering economics. Thank you guys. See you guys soon in a couple of hours. Okay. Don't worry. From tomorrow, I'm going to do every day what I will stop solving all these bonds because right now I'm kind of rushing and to catch up. So for tomorrow, I'm gonna start slowing things down. Okay. Thank you guys. Bye.